Uh, Hello friends. So today we are going to study the Bayesian inference. So I hope everyone is familiar with what Bayesian inference is actually it. So first I will start by defining what's the Bayes formula is. So we will consider it for a continuous case. So let's say we need to find a posterior distribution of some unknown parameter theta given we have some existing information. Then we can write the posterior distribution of the parameter as follows. So we will write theta of phi of theta given x is equal to joint density, that is your f of x given theta, into the density of parameter. In denominator we have the marginal density, that is f of x given theta dash into pi of theta dash. So here pi of theta is our prior density, that what we believe, uh, that is our, we can also call it is our belief in theta before seeing the actual data, that is our x. F of x given theta is our likelihood, or you can also call it as our joint density. This is our probability of observing theta, sorry, this is our probability of observing our data given that our theta, that is our belief, is true. And then in denominator we have the marginal density of the data. So we can also consider this as a normalization, so that our posterior integrates to 1. So this works as a normalization. So this is for a continuous case. So when we are going to consider a discrete case, so we are going to use our summation symbol. So now just to have an example how to find the mean and variance of the unknown parameter here. So we want to say that once we know that what is our posterior density, let's say pi of theta given x, that is our posterior density, or we can also call it our updated belief over theta after seeing the data x. So what Bayesian actually does is that we have some prior belief, that is your pi of theta, and you are updating this belief using some, you are updating your belief and using some data, and it resulted in your posterior density, that is your posterior belief we denoted it using pi of theta given x. So this is all we call as a Bayesian update. Okay, so we are going to learn this transition as a learning process. So now we are going to summarize our posterior. So what are the better summarization measure than our mean and variance? So first, obtaining our posterior mean. So our posterior mean is given as integration from minus infinity to plus infinity, or theta of, that is our posterior density function, and theta. Similarly, our variance is also similar, that is integral of, let's say, sorry, variance of theta given x is also similar, that is our expectation of uh, theta minus e of x, that is our theta given x. square given x. You can also write it as an integration formulation, then like integral of, let's say, theta square x, theta square density of our theta x, uh, d theta minus expectation of theta given x, that is our mean square. So this is all about our posterior mean and posterior variance. So we have seen how the Bayesian inference works. So we have a prior knowledge. We have seen the data, and we are updating our beliefs using the data, and that's reflected in our posterior density function. That's all about our basic Bayesian. So now let's try to obtain uh, for now let's try to obtain the inference for normal distribution. Now let's say we have a data. Let's call this data as x1, x2 till, let's say, xn. This is IID distributed data, and let's call it this as a normal distributed also, like the mu and sigma square. Now let's assume that your mu is unknown and sigma square is known. So we have prior knowledge that, let's say, mu follow some distribution. Let's call it as a mu follow the normal distribution with mean eta, and let's say the variance tau square. Now let's say we already have an existing data of 10 points, that is our n is equal to 10. And now I want to find and derive the distribution for mu here. Given that I already have a data of 10 points and my sigma square of that distribution is unknown, sorry, it's known. So I'm going to derive how the likelihood function that is unknown in many given textbooks. So here I'm going to try how to derive the likelihood. So the likelihood is generally given as I think in a very convenient way. Let's say that we have a joint function f of x given mu. I will write the likelihood function, that is under root of 2 pi sigma square, it is exponential of, let's see, 1 upon 2. Now this is a likelihood function for the normal distribution. Now for the sake of convenience, since this is conditioned by mu, we are going to ignore the constant term and which are not dependent on mu. So basically we are going to ignore this constant term, and we will write the equation once again. That is, now we can say that this is proportional to product of exponential of bracket square. So I will simplify it further. That is our exponential of minus 1 upon 2 summation of sigma square constant x minus mu bracket square. Now this identity summation of x minus mu bracket square, I can further simplify this as summation of x xi minus x bar square plus en into x bar minus mu bracket square. So I will just try to substitute in the original equation. So now we have likelihood of f is proportional to exponential of 1 of half multiplied by summation of this whole term exi minus x bar plus n into x bar minus mu. Now since this term is not dependent on mu, we can further ignore this term and I will write this as a constant function. So now we have our final term, that is exponential of 1 upon twice sigma square into n into x bar minus mu bracket square. So this is our likelihood function of mu, which quite looks like the normal density function with mean x bar. If we are rearrange this term as, let's say, n into mu minus x bar square. So this resembles our normal distribution with mean x bar and variance sigma square. This n will be out there, so it's sigma square upon n. So you can say so. Now let's consider our prior, that is mu. It is distributed at normally with your mean eta and variance, that is tau square. So we can write the likelihood for mu as, let's say, pi of mu is proportional to the likelihood of exponential of minus 1 upon 2. So the variance is sigma tau, so tau square in bracket mu minus eta is there, so eta bracket square. So this should be the likelihood for our pi of mu, that is density of mu. And now let's try to find out the posterior via the Bayes. That is, we want to multiply our likelihood and pi. That is, we want to find our posterior, that is the density form. Posterior density, that is pi of mu given x, that is proportional to our joint density function of f of x given t, f of x given mu multiplied by pi of mu. So we will write this. So we already know the likelihood for this and this also. So we will try to combine this, that is exponential of minus 1 upon 2 sigma square n multiplied by mu minus x bar square into, now the likelihood of mu, that is exponential of minus 1 upon twice tau square multiplied by mu minus eta bracket square. Now we will try to expand this, so it will look like this something. So exponential of, we will take common 1 by 2 1 by 2. Now we are left with n into mu minus x bar bracket square upon sigma square plus 1 upon tau square multiplied by mu minus eta bracket square. Now expanding this further, that is, we have n into mu square minus twice mu x bar square x bar n minus x bar square upon sigma square plus mu square minus twice mu eta plus eta square upon tau square. Now taking the common term aside, that is exponential of minus 1 upon 2. So now we have two common terms, uh, that is mu bar and mu and mu. So we will take this term up aside. So now we have mu square, in bracket we have n upon sigma square, and now here we have minus 1 upon tau square. Similarly, taking out the mu, that is plus only mu, let's take minus mu out, then we are left with n x bar upon sigma square, and here it is plus, it will be twice mu, sorry, will be eta upon tau square, and plus we have this term constant, that is x bar mu bar. So let's start with x bar square upon sigma square plus mu square upon tau square. Now these are the constant terms which are independent of mu, so we can also write this as a constant, or we will simply ignore this. Now for the sake of convenience, we will substitute these two terms with, let's say, a, this in with b. So rewriting these terms again, now we have exponential of minus 1 upon 2 given mu square, writing this as the a. So now we have a minus twice mu, this is b, so b plus this something constant, so let's let we have c. So this is our constant, we are writing this as a c. Now can we arrange this whole term to resemble the likelihood of normal distribution? So yes, we can rearrange this. Rearranging this, so now we have, so I will try to reframe this as a proper square. So first I will take out the a. So now after taking out a, I will just write it here and I will square this. So now I have a upon 2, I'm taking the function, so mu square upon twice mu b upon a plus some constant c. Now I can write this as a quadratic form, that is minus a upon 2 mu square minus twice ub. So I can simply add twice ub upon a. So now I can simply add, let's say, plus b upon a bracket square. So adding this, I will subtract also b square upon a square plus c. Now this is also independent of mu, so we can just ignore this or keep it as a updated c dash. So now this, that is our exponential of minus a upon 2 given mu minus, that is 2 mu, that is mu, sorry, b upon a bracket square plus some constant. I am ignoring it. We can simply ignore it as this is independent of mu. So now this a upon 2 given mu minus ba. This resembles to the normal distribution with mean, that is b upon a, and variance, that is 1 upon a. So now we have the posterior distribution such that the mean of posterior distribution is b upon a. Now, sorry, just mu upon, this is mu given x, that is b upon a. Now we know our b, so our b is so now our b is n into x bar upon sigma square plus eta upon tau square. In denominator we have n upon sigma square plus 1 upon tau square. Now we will try to simplify it further. That is n into x bar upon sigma square plus mu into tau square upon n into sigma square plus 1 upon tau square. Sorry for repeating this. So generally what happens, we calibrate tau as sigma square upon m. So I will just, so we need to substitute sigma tau as a sigma square n. So we can just write it like this: n upon x bar upon sigma square minus mu into m upon sigma square upon n upon sigma square plus m upon sigma square. So if you solve this, it will result in like something like this. That is all sigma square will be gone. It will like m in x bar minus mu eta m and into n plus m. Similarly, our variance, that is theta given x, here theta is mu, so you can simply write this as a variance of mu given x, that is, it was simply given as 1 upon a from our distribution. So now, so we can simply write this as 1 upon n upon sigma square minus m upon sigma square. So I'm directly substituting tau as a m upon sigma square. So now we have sigma square upon n plus m. So that is our variance. So now this is our variance and this is our, sorry, this is all, there is no minus, so it will be a plus. Sorry for the mistake, but this will be our mean and this is our variance. So this is how we have calculated the mean and variance for our posterior distribution.